So what is shift registers? Shift registers are a type of sequential circuits. Okay, so shift register are also the sequential circuits mainly for storage of digital data. Okay. So you know that the basic entity that stores a bit is a flip-flop. Okay. So definitely the registers will consist of multiple flip-flops. Okay. So they are a group of flip-flops connected in a chain so that output from one flip-flop becomes the input of the next flip-flop. Most of the registers possess no characteristic internal sequence of states. All flip-flop is driven by a common clock and all are set or reset simultaneously. Okay. So simply you can think that shift register is a combination of flip-flops which connect to the same clock. Okay, and there are different connections which makes them the serial register, serial input, serial output, parallel input, parallel output. Okay, serial out, parallel. There are a lot of combinations. Those are written here. Okay, so serial in, serial out means the input will go serially, the output will come serially. Okay, means we cannot change all the outputs at once. It will change in serial manner. Then there can be serial in and parallel out. Then another option is parallel in and serial out. Okay. Then parallel in and parallel out. So all these are the combination possible. Okay. And bidirectional shift register means we can transfer data from both sides. A special form of counter, shift register counter, is also introduced. Okay. So there are some also uh, counters which are called the shift register counters. Okay. So the counters that we studied in the previous section are not based on shift register. Okay. So we will not study this last part. Okay. So what is a register? As you know, a set of n flip-flop. Okay. If there are n flip-flop, normally we say it is n-bit register. Okay. A set of n flip-flops, we say it is n-bit register. If it is 8-bit, so we call it 8 bit register. So there will be 8 flip-flops. Okay. As you already know that each flip-flop stores 1 bit. Okay. So this you already know that each flip-flop can store only 1 bit. Two basic functions: data storage and the data movement. Okay, so register will have one more thing, that there should be a data movement. Okay, you know that a flip-flop can store the data, but in register, what we need to have a data movement, a shift register. Okay, so this is a basic definition of a register. So what is a shift register? Okay, so the definitely shift register is a register that allows each of the flip-flop to pass stored information to its adjacent neighbor. Okay, so in the shift register allows each of the flip-flops to pass the stored information to its adjacent. So whatever the nearby flip-flop is there, so the previous flip-flop will transfer data to this flip-flop. Okay. So how it will happen, we'll see this. So what are the counters? Normally the counter are register that goes through a predetermined sequence of states. So counters basically that we have seen the counters. Counters are also shift registers. Okay, but their states are predetermined. Okay, so a register that goes through a predetermined sequence of states. If it is a up counter, it will count serially, and if it is down counter, it will down from the present number to the lowest number. Okay, so the counters have the predetermined states. So this here some example of the registers has been shown. Okay, so you can see in the first one the data is going inside from here, and it is coming outside, and you can see internally data is shifting like this. Okay, it seems similar to the counter as well. So this is what serial in shift register and serial out. So serially data is moving. It will go to the first flip-flop, then it will go to the second, then it will go to the third, then it will go to the fourth. Like that it will continue. If it is 10-bit shift register, so you can have a 10 serial moving data. Okay. Then it can be serial in. So okay, this is shift right as well. Data is moving to the right side. Okay, and here it can be similar thing, but the data is moving to the left side. So this is called the shift left. Okay. Third thing is the parallel in and serial out. Now you can see that each of the flip flop, you consider this block as a flip flop, one block as a flip flop. Each flip flop is getting its data separately. Okay, each flip flop is getting data input as separately, but the data is moving serially. Okay, so they will get data parallelly. Each flip flop is getting different data input, but their data cannot move directly here. We cannot take the data outside. We are not taking data outside directly. Rather, we are moving the data from one to second, second to third, third to fourth, like this, and then it is coming out. So this is simple parallel and serial out. So this is very simple. Only by this block, if you replace this block by a sorry, flip flop, this will become a resistor. Okay. Then we have another class, serial in and parallel out. So data is going serially. Okay, not all the flip flops are getting data individually. So all the flips are not getting data individually, but data is coming individually. Okay, you can see that we are taking data outside individually. Okay, so this is serial in and parallel out. Okay, then there is data in. All the data is going parallelly, and all the data we are tapping out parallel. So this is parallel in and parallel out. Okay, so rotate right. You will see all these things in the microprocessor labs also. Okay, so these are rotate right. So you can see the data is going from left to right to right to right, and when it is to the rightmost flip flop, it comes back to the leftmost flip flop. So it is the rotate right. Similar thing happens for the rotate left. Data is moving from left to right, left, 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 and then it comes back to the leftmost. Okay. So these are the different operations that are possible using the shift registers. Okay, I hope everyone is clear about this operations. Okay, so storage capacity, as already discussed, storage capacity of a register is the total number of bits. Okay, so I told you that how many bits a register can store, that is called the storage capacity, and you already know that each flip flop can store one bit. Okay, So if we are using the 10 flip-flop, the storage capacity is 10 bit. If we are using 5 flip-flop, the storage capacity is 5 bit. Okay. So how many number of stages we are using determines its storage capacity, means how many flip-flops we are using. Okay. This no need to tell you, just a reminder, this is a D flip-flop and this is a D flip-flop. If we apply an input of 1 here, okay, this we have applied input 1, so the output will remain same. Okay, D flip-flop, if you remember the table, D flip-flop is like mirror. Okay, so if the input is 0, okay, and the clock comes, so the output will change to the 0. If input is 1 and the clock comes, the output will change to the 1. Okay, so this is like flip-flop. So this is happening, the state is changing only after the appearance of the clock. Okay, so if the input remains 0 and the multiple clock comes, the output will not change. Whatever is the input side, it will change it to the output side. So you can see this is a positive edge triggered here. Okay, it can be other place negative edge triggered also, that doesn't matter. Okay, so this is a flip-flop, both D flip-flop. Okay, so mostly we'll be using the D flip-flops in the resistors. Okay, because whatever the data input you give, the same is passed to the output. That's why we prefer to use the D flip-flop here. Okay, and we can make the D flip-flop using the JK flip-flop as well. Okay, so this is like, if we from the JK flip-flop, if we want to make the D flip-flop, so like this is like this is J and this is K. Okay, if we connect J and K like this, so okay, so what happened? Okay, so by using J and K flip-flop, we can connect and we can make the D flip-flop. Only there is an inverter between J and K that makes it D flip-flop. Okay, so whatever the input we give at the appearance of the clock, the data will pass to the output side. So this is how the data will be transferred from the input to the output side. Okay, so we talk about serial in, serial out shift registers. So I think you have seen this type of shift register. The data that is 1 bit at a time on a single line. Okay. So the serial in, serial out shift register accepts data serially. So remember this, only 1 bit can go inside. Okay, you can supply only 1 bit at a time. Means at each clock you can supply only 1 bit. At each clock. Okay, so at each clock you can supply only 1 bit from the input side. It produces the stored information on its output also in serial form. So output is also serially available. Okay, so this is the data input. Okay, so this will be either 1 or 0. Okay, so this will be either 1 or 0. So and this is the output side. Okay, if you want to tap out the data, suppose we stored some 4 bits in this. Okay, and we keep and we leave it. Okay, we are not taking anything outside. We stored 4 bits, data is stored, and we are not tapping outside. Okay, let's say after some time we want to take the data outside, so this is the point where we have to take the data out. Okay, so clock will come, the first bit will come outside this. Okay, FF3 bit come outside. Then this bit move here, this bit will move here, this bit will move here. Okay, then again we tap the clock, the data will come again outside. So like this it would continue and the data will be keep popping out. I have not explained till now about the functioning of this. Okay. So how we start? Okay, initially we do not know at what state these flip-flops are. So what we do? We press the clear button and all the flip-flops become clear. Means the output of each flip-flop becomes 0. Okay. So initially we press this clear. So or the output becomes clear. So 0 here, 0. This is 0. This is 0. This is 0. Like this all are 0 once we press the clear. Okay, so let's assume we can assume some input data. Okay, let's assume that what data we want to input to this flop is 1101. Okay, so this is the data that we want to insert in this flip flop. This is the 4 bit. So we want that this flip flop should remember this data. Okay, so what input we will provide here? So from this the first one will come here. Okay, first one will come here. Then what will happen? So as soon as the one comes, one is available here. Initially all flip-flops were 0. Okay, now the we change data input to 1 and the clock appears. As soon as the clock will come, this D output will reach, this D input will reach to the output and this will become 1. Okay, and this D will become 1. What about this? So when the clock came, this was at that time this Q was 0. So this was 0. So the output will for this will be 0. This was also 0. So this will also remain 0. This was 0 and here the output will also be 0. Okay. So what happened in the first clock? In the first clock, the data remained only for the first flip flop. FF0 has changed to 1. Okay. Then we insert 0 here. Okay. The second bit that is appearing here is the 0. So what will happen as soon as the clock comes? Now the 0 is the input. So as soon as the clock comes, 0 is here. Okay. And the output clock comes, this will change to the 0. Okay. When the clock came for the second flip flop, the input was 1. Okay. Now the input is not 0. So the input was 1. So 1 is available here and the second clock comes. So this 1 will reach to the outside here. Okay. So this is the state. If I draw the state of the circuit and since 0 was here, so 0 will move here, 0 was here, so 0 will move here. So what is the state of the circuit after the first clock? So this is how the state of the circuit after the appearance of second clock. Okay. Then comes the third clock and the third input data. So it is like 1 here. So as soon as it is 1, so let me remove some of the parts. Okay. So now the 1 is here. So 1 will appear here. And this is the current state. This is the current state. Okay. So as soon as the 1 comes, so what will happen? This one. Okay. The second one comes. What will happen? This will change state to 1. Okay. It was 1. This was 1. So this will be passed to the next flip-flop and the state of this flip-flop will become 1. Okay. Before 1 came here, it was 0 here. Okay. So here it was 0. Initially it was 0. So the clock comes. So this will change to the 0. Okay. And the 1 moves here. Okay. So what is the state now? So this is the state of the this is 0 and this will remain 0 because previously here it was 0. It will remain 0. Next count comes, this 1 comes here, again this 1 will appear here. So you can see that what is the current state? It is 1 0 1 0. This is the current state. Now the 1 appears here. So what will happen? This 1 will move here. So here what will get the 1? Okay, let me use a different color. So this 1 comes here. Okay, this one was here. This one will move here. Here it was 0, so this 0 will move here. Here it was 1 and this 1 will move here. So the current state is 1 1 0 1. So now we have entered the 4 bits in this flip. I hope you understand. Okay. So now the states of the flip flop is all flip flop has what we want to have. Okay, so the data stored in this register 4-bit register is 1100 which we want to store initially. Okay, so if I remove everything, so what we have a 1 1 0 and 1. The input data was 1 1 0 1. Okay, so these stored the required data. Now we will stop the operation because we want to store the data only. Okay, now we have stored the data. Suppose if we want to take the data outside. Okay, if we want to take the data outside. Okay, so since it is a 4-bit data, so we need to use the 4 clocks and the data will come out. Okay, so we can keep here 0. Okay, so constantly we can keep it here 0. Okay, so when the first clock comes, what will happen after? Now we are taking the data outside. Till now the data is in the registers only. Okay, so we can take this data out. The first data we can take directly outside if we want. Okay, so this one is here. So as soon as the next clock comes, what will happen? This 0 will move here. This 1 will move here. This 1 will move here. And this 0 will move here. Okay, so the next state is like this. So 1 is already available, so we have taken that 1 already outside. So now what is output available at the output is 0. So we have taken 0 here. Then again next clock comes. Okay, so we keep this data input data as 0. Okay, so what will happen? This 0 will come here. This 0 will come here. Okay, this previous state was here. This 1 will come here and this 1 will come here. It means this 1 is available here. So only after 2 clocks we have 3 data out because the first data is already outside. Okay, so again the input is 0 again. Input is 0 again. So what happens? Input is again 0. We have kept the input constant to 0, so the 0 moves here. Okay, so the 0 moves here. This 0 moves here. And this 1 moves here. So what we have now outside is 110. So this data is available outside. I hope you can see that the data that we have inserted has moved serially from one to the last, and data when we want to take it outside, the data came serially, not at once. Okay, so this is a 4-bit serial input and serial output register, shift register. Okay, if you have any doubt, any confusion, you can ask in this regard. I hope you understood it. So if I ask you to make a 8-bit shift register, serial input, serial output shift register, you can make it. If I ask 5-bit, you can make it. Okay, and you can explain the operation for any size of the shift register. Although the basic operation is written here, okay, so you know that. So this we have already done. The LSB has shifted from the FF0 to the FF3. So like this we have already done. Okay, so data input can be different. Okay, so if I ask you, I give you a different data input and ask you to show all the states, how the data moves within this register, then you should be able to show it. Okay, so this is all like this. It has been shown here. Okay. Another method that we can use to show the data can be important. Okay, it is like in the form of the table. Okay, so let me show you that we want to. That also makes things sometimes. Let's say this is I have to give names. So let's say this is Q1, Q2, Q1, Q2, Q3, and Q4. Okay, so let's say these are the Q1, Q2, Q3, Q4, and this is the data input. Okay, so let's say this is the input only, IN. Okay, so how we can show this operation? So what we have the inputs are input Q1, Q2, Q3, and Q4. Okay, these are inputs and these are output as well. Okay, so input is only IN and others are output as well. Okay, so let's start from here. So what was intended data that I shown you 1101. Okay, so one more thing is there, that is the clock. That is the clock. Remember, everything will change only after the clock appears. So initially what the inputs will have the data, what data input will have is 1. Okay, initially all are 0, all are 0, all are 0, all are 0. Okay. So this Q4 is also the data output. Okay. This is another format we can do the same operation. So what will happen as soon as the clock comes? Okay. So initially this was input was 1. Okay. Uh, so so this was the initial state. All the 4 bits were 0. Input was kept 1. Okay. Now the clock comes. Okay. So what will happen? This will move right like this. So this will come here 1. This will come here 0. This will come here 0. This will come here 0. And this will go out. This will change to 0. Okay. तो ये कहीं जाएगा नहीं, ये अपनी पोजीशन पर चेंज हो जाएगा. ठीक है. So this won't go anywhere, but this will change at its position to 0. ठीक है. ये मूवमेंट नहीं है, ये बस ये क्या हुआ, चेंज हो गया वहीं उसी पोजीशन पर. ठीक है. तो लास्ट वाला जो है Q4 वो कहीं मूव नहीं कर रहा है, क्योंकि आप देखें आगे कोई कनेक्शन नहीं है, तो ये वहीं उसी पोजीशन पे क्या हो गया, 0 हो गया. Then हम ऐसे भी दिखा सकते हैं इसी मूवमेंट को. Then you know that the next data is what? 0. The next data is 0. Okay. So this has changed in the previous state and this is also changed to the next state. Now the data input is 0. What will happen? Clock comes, this 0 will move here, this 1 will move here, this 0 will move here, and this 0 will move here. Okay. Similarly, this will continue. So what will be the next data? Next data input will be 1. So as soon as the clock comes, this will move here, 1, this will move here, 0, this will move here, 1, this will move here, 0, and the next data is 1. And in the next cycle, this will change to, and in the next cycle, this will change to, so this will, the clock, this will change to 1, this will change to 1, this will change to 0, and this will change to 1, and like that you can see that we have got 1101. Okay, so like this we can draw by using a table as well. Okay, so same operation we can understand by the table as well. I hope this is clear to all of you. Okay, so same operation but in a different format. Okay, we have seen that. Okay, so this has been shown like that. You can see it. Okay, so this is another example. 4-bit being shifted from left to right. So you can see this if you want. Otherwise, you know it how we can do it. Okay, no need to worry for that. Okay, this is again a 4-bit shift register. Serially shifted out of the register. So I have told you the shifting in, how we are shifting the data inside, how we are shifting the data outside, both operations, and I have told you, and all the replaced by zeros. You can see that while shifting out, I have connected a constant 0 to the input side. So the input was available at the out. Okay. So, so this is 5-bit serial in serial out shift register. I think you can do it by yourself. Okay. So next thing is serial in parallel out shift register. Okay. So the only difference that we can see here is, let's see the some theory lines. For this kind of register, data bits are entered serially in the same manner as discussed in the last section. So what is this? This is where it is gone, serial in. So data will come inside serially as it came out previously. Okay. So data input format will remain same here. Okay, the difference is the way in which the data bits are taken out of the register. Previously, we were taking data out of the register by serial out. Okay, at each clock, the data was moving from left to right like this. At each clock, the data was moving. But the difference is here is the data we are how we are taking the data outside. Once the data are stored, each bit appears on its respective output line. Okay, this is clear. Okay, at each flip-flop output we get the value of each bit what we want to store. Okay, and all bits are available simultaneously. Okay, you can see that all the bits are available. A construction of 4-bit serial and serial out is shown here. So what is the difference here is, what is the difference here is the data we will enter from here. Okay, serially how we enter data, you know it. So we will serially enter the data. Okay, now the data has been entered, so q naught has MSB, Q1 as next to MSB, then next to the LSB, then this is LSB. Okay, so this data is available. Okay, now we want to take the outside, so we can connect directly to the output line directly. Okay, where we want to move it here, so we are taking the data outside directly. All the bits we are connecting where we want them to be used. So we are connecting them directly. So we are taking, this is the parallel out. Okay, we are not moving data anywhere. Simply we are taking the data directly outside. Okay, so this is how. So this output operation is simple. Okay, so there is no clock required for the movement of data from input from the stored register to the outside. Only the clocks are required when we are inputting the data. Okay, so this is the difference that we have in the serial in and parallel out registers. Okay. Okay. So for today, this is enough. Rest of the portion we will see in the next class.